Natural convection. Welcome back, everybody. We'll continue with our studies of heat transfer by convection, driven by velocities that are induced by differences in buoyancy and not by an external applied force. We have seen enough things that enabled us to take on a very interesting problem. And the problem I want to discuss is this one here. Let's see. I took this photo in my previous house in which it was January, and we see the window that is clear on top and has frost in the bottom. Actually, in this case, it was even like frozen, but sometimes we see condensation. And the question is, why? And we can tackle on this, and I think it's going to be awesome. So, is it because, I don't know, liquid water, solid water is heavier than vapor, right? There are many things we can think about, but if we think deeply, we realize that no, it's not that the ice crystals are rolling down the window. It's not that water is dripping when there is condensation, but we know some other things. So let's take a look at this. And we go back to what we discussed on Monday, and is we would have in these vertical plates, such as the window, we would have a boundary layer that forms. In this case, it's a hot plate, and the boundary layer goes up. If the plate was colder than the fluid, the boundary layer would be the opposite, would be with the flow coming down. And here we have this expression of Nusselt that says Nusselt is proportional to this Krasov number, which we discussed. Krasov number is somewhat similar or analogous to the Reynolds number. By the Reynolds number, we have a known velocity that is the one that drives the flow. And in the Nusselt, in natural convection, we do not have an external velocity. So this Krasov number accounts for the effect of gravity, volumetric expansion, and temperature differences. So no temperature difference, no flow. We knew that. No thermal expansion, no flow. We knew that. No gravity, no flow. And that's the example I mentioned to you about people doing experiments in Skylab, in which they couldn't play with beta because it was a material property. They couldn't play with delta T because it was a process parameter, but they could play with gravity. And they were making semiconductors in space. Super interesting. So Nusselt is proportional to Krasov to the 1/4. And because Krasov is proportional to the, in this case would be, let's call it, this is a local convection coefficient, local. At each point in X, we have a different convection coefficient. So Krasov of X would be proportional to the X cubed, right? So X cubed to the 1/4 Nusselt, and let's put this. Okay, here we go. So we have Nusselt of X is proportional to Krasov of X to the 1/4, right? And we knew that Krasov of X was proportional to the proportional to X to the cube. So we have Nusselt of X is proportional to x to the 3/4. Oops, that should be a 3. X to the 3/4. And so going back to the type of things we knew from the quiz 3, we know that the thickness of the boundary layer, of the thermal boundary layer, is was x over Nusselt. Therefore, the thickness of the boundary layer would be proportional to x to the 1/4. This looks like a bunch of math, but let's take a look at this. What it says is that if we have our vertical plate here, and we have a boundary layer developing, this thickness, this is yct proportional to x to the 1/4, and x was moving in that direction. This means proportional. So, okay, so it's getting thicker and thicker. And we know that the thicker boundary layer would give us a more insulating, more insulation to the heat transfer. So if here we are at T infinity, right? And here we have an amount of heat transfer. The temperature difference is going to be small where the boundary layer is thin, and thick where large temperature difference when the boundary layer is thicker. Okay, so that we already knew. I went very quickly about it, so perhaps you feel, whoa, we're going super fast. But if you rewind, all these type of things we had already discussed. The only thing that is new is that we said that the thickness of the boundary layer increases with x to the 1/4 for a flat plate with forced external convection was x to the 1/2. But although one is 1/4, the other is 1/2, it's more or less the same thing. It's something that increases quick at the beginning and then keeps rising at slower velocities. And the boundary layer is an insulating layer just as before. Now, if we go back to our photo of the window, we see if we go back to, so let me see what happened here. No. Wow. I'm struggling trying to delete this. So let me see. So let's come back up. Wow. Okay. Hmm. Gosh. Well, I don't know. Hmm. Okay, fine. So, somehow I'm unable to do it. So we'll need to, I'm going to recycle this image here. So, wow. God. Okay. So, um, okay. I'm somehow unable to draw. No, now I'm able to draw. So, damn, what happened? Wow. I don't know. So, it's, wow. Anyway, so in if we imagine the window is made out of the two panes, let's think of a single pane window first, single pane, and we did so many of those. The outside of the window is against cold air, and the inside of the window is against the hot air inside the house. So how can it be? And so let's see. Okay, let's see if it works better now. Okay, so let's hope it works. God. So if you guys want to check with your microphones, in addition of like this thing not working, is we have some soundtrack. I don't know if it is really intended. Okay, so if we think of a single pane window, the outside of the window is against the cold air. The inside of the window is against warmer air. The window will be at some intermediate temperature between the outside and the inside. That means that from the point of view of the air outside, the window is hot, But from the point of view of the window, of the air inside, the window is cold. So outside, sometimes we have a little bit of wind, so we're not going to worry very much about what's going on outside. But from the point of view of what is inside, it is very interesting because the warm air inside the room hits the window and comes down. And as this warm air that of the room is against the window and creates a fluid flow downwards, it's also developing a boundary layer in the window, right? As it moves down. This boundary layer is going to be thinner at the top, that is the leading edge, and it's going to be increasing in size as it comes down. And how is it going to do it? Increase in size with this x to the 1/4 growth profile. So we're going to have at the top a very thin boundary layer, and at the bottom, we're going to have a thick boundary layer. At the top, thin boundary layer inside, and at the bottom, a thicker boundary layer. So now let's think of this. If we remember the overall heat transfer coefficient, and we remember our calculation of thermal resistance, what we are going to have is that the top of the window is going to be at a temp, because it has little thermal resistance to convection, it's going to be more or less at the temperature of the room. And there is no frost in here. As we move down the window and the boundary layer gets thicker and thicker, then it's going to be more and more, the window is going to be more and more insulated from the room temperature, and the window is going to be colder and colder because part of it goes against the outside, right? And is separated from the inside by an ever thicker thermal boundary layer. It gets to a point that the surface of the window can reach like the dew temperature, or can reach 0 degrees. And in this case, it's 0 degrees, and that's the frost line. This line here indicates that the heat transfers through the window is such that the temperature of the surface of the window, which is an intermediate temperature, right? We have convection in the inside, we have the glass, and then we have convection on the outside, right? We know how to calculate all these based on the concept of thermal resistance. And it gets to a point in which the thermal resistance of convection is so high that the surface of the window is below freezing. And in that case, that's what we see. And it's a fantastic way of understanding what's happening. And it says so much about mirrors sometimes fog up this way, right? This help us understand something we see every day that is not obvious. I was hoping to do some sort of schematic, but I don't really know what's going on. That oh no, so this would be our window. We can say this is outside. We can say this is inside. And so if this is the top of the window, the boundary layer is developing this way. And we have this thickness that increases. And we have here the infinity of the room, right? And an amount of heat that comes out. We can calculate all these based on our understanding of thermal resistance of week 5 of class. And if we combine this understanding of thermal resistance with this formula here, that tells us what the convection coefficient is going to be at each point on the window, we can predict exactly at what point this is going to transition, reach 0 degrees and have the frost line. I think it's amazing that we can do this, and we can explain things and predict them scientifically. And there are things that intuitively we would have never guessed, right? It's so much easier to think like the heavier water or ice grows at the bottom, but that's not the reason why it is at the bottom. So last class, we also did a calculation example for the convection coefficient of a chimney in still air. If everything goes right, I want to retake this example late at the end of the day today or tomorrow to calculate what happens when we have mixed natural convection and forced convection. But before we do that, let's study other examples of convection heat transfer. We talked about the vertical wall only so far. I'm going to skip on the constant heat flux. But let's see what happens when if the plate, instead of being vertical, is inclined. Now, if it is inclined, we have two possibilities. Let's say that the plate is hot. If the inclined plate is hot, that means that would be this case here. That means some air that wants to go up just presses against the plate, right? And as it presses against the plate, it grows a boundary layer. But the top side of this hot plate, the hot air wants to go up. And it does it in a very different way than at the bottom, because at the bottom, wants to go up, finds the plate, and creates a boundary layer. On the top, there is no, wants to go up, and there's nothing resisting it. So essentially, it goes up in the form of turbulence. Similarly, if the plate was cold, we would say the same thing. So now we have two heat transfer coefficients to worry about. A heat transfer coefficient that would be in the compressed part that develops this nice boundary layer, or the heat transfer coefficient that develops in the free part that has this turbulent motion. Before we, well, okay, so in the part of the boundary layer, the part of the boundary layer here, we can calculate it quite easily because it's essentially the same as a boundary layer on a vertical wall, except that the value of gravity now is not the same because we have to account for the value of gravity in the direction of the plate. So we have to multiply the gravity by the cosine of theta. So when it's vertical, theta is 0, cosine of theta is 1, and it's the formulas we know. If it is a little bit inclined, we start to multiply by this cosine of theta, and the more inclined it is, the smaller the apparent gravity would be. So the compressed part of an inclined plane, everything we already knew. For the free part, there are no general correlations, not for inclined plates, right? But let's talk about the case that is so inclined that is flat. Now, if it is flat, yes, we can say things. So in the compressed side, right? Let's say it's a hot plate, and we look at the lower side, right? We have a correlation that goes with Rayleigh to the 1/5, right? For the compressed part in this case. For the free side, the side that develops this turbulence, we have two calculations. One depends on whether the fluid is more like a wake, wouldn't be really laminar, but it's low turbulence, or if the fluid would be really turbulent. I guess what we see that in this case, the correlations is a constant times Rayleigh to an exponent. And this is the way most heat transfer natural convection correlations look like. These are empirical, but the 1/4 is the type of exponent we found in laminar convection, and this 1/3 is what we used to find in turbulent convection. Okay, kind of makes sense, and we know what to anticipate. And the Rayleigh is based on L. So say we have a circular plate, that would be the diameter. But if we have a kind of a random shape, then L is defined as the area divided the perimeter. And with that, we can generalize for different shapes. Something that is to be expected is that is what side of the plate will lose more heat, if the top side or the bottom side. Say that the plate is hot, so the top side is a free flow going up, and the bottom side is a flow that is developing a boundary layer as the hot fluid comes in contact with the plate. The one that is more that has a cleaner flow, that is at the bottom, that tends to have a lower convection coefficient. For example, if I calculate for Rayleigh of 10 to the 6, right? Rayleigh of 10 to the 6, I would be comparing this correlation for the upper side of a hot plate and this other correlation for the bottom side of a hot plate. And guess what we see? That the free side, that is the one that develops the higher turbulence, has a higher Nusselt number, higher heat transfer. That's very interesting. And this is in keeping with all the things we have seen so far, as turbulence enhances heat transfer, how a laminar boundary layer has lower heat transfer, how when we have flow separation, like in the wake behind the cylinder, we start to develop turbulence that enhances the heat transfer. We see all these things, these same concepts in action and again and again. From the practical point of view of getting a number, it's always the same process. We have to calculate Rayleigh. Then based on the proper Rayleigh number, we calculate a Nusselt number, and this problem is very easy. And based on Nusselt, then we unpack it to calculate a convection coefficient H. Always the same process. From the plug and chug point of view, this is trivial. What is interesting is trying to anticipate what we should see. So when we are engineers in the field, or when we're managers trying to assess what the engineers say, we don't need to worry so much about making the calculations ourselves, but as to making sure that what they say matches our expectations from understanding. Let's talk about cylinders as promised. And here we have this correlation for horizontal cylinders that depends on the Rayleigh number and the Prandtl number. In the past, we saw correlations for forced convection and horizontal cylinders and depended on the Reynolds number and Prandtl. Now we have Rayleigh and Prandtl. And very interestingly, both expressions are very similar, in which we have something that depends on Rayleigh in this case, and we used to have something that depended on Reynolds. And we have a term that is a small constant. And this small constant says when the Rayleigh number is small, or when the Reynolds number is small, either of those things mean that the fluid flow is very small, is low. And if fluid flow is small, we start to have more of a problem of conduction more than convection. And when the fluid was zero velocity, essentially is pure conduction. And although for zero velocity, these correlations are not right, for zero velocity, they are not. For very small values of velocity, they are good. And this 0.6 value is what accounts for these conduction effects happening. you see that this is raised to the square. So this coefficient square, this 0.36, for the point of view, for the correlations of cylinders on transverse flow, the coefficient was 0.3, very similar, right? 0.3 when Reynolds was 0, that was 0.3. And now when Rayleigh is 0, this is 0.36, more or less the same. This is empirical. This doesn't come from solving any differential equation. This comes from a poor student who spent 4 years putting pipes in air and water and oil and running an experiment, taking notes, realizing everything is wrong and doing it again 1,000,000 times. We have another, in addition of this expression, we have this other one that is simpler to use. This is kind of more general in the formula, and this is simpler to use but requires a table. And says Nusselt, the average Nusselt based on the diameter is constant times Rayleigh to an exponent. Look at this. When the Rayleigh number is very high, we have an exponent of 0.33. That's the same exponent that corresponded to a vertical plate in turbulent flow. We see this analogy that is very similar to external flows, in which what is turbulent or what is laminar tends to have an exponent that stays more or less the same regardless the geometry. So for the case of the sphere, of the cylinder, we have this 0.33 for high Rayleigh numbers. If the Rayleigh number is lower, we have 0.25. Guess what? That was the exact exponent that came from this time, yes, solving the differential equations for a vertical plate. So these two exponents make sense. What these coefficients are here, these are the empirical part. Now, when the Rayleigh number becomes smaller and smaller and smaller, that means the temperature difference is smaller and smaller, or the gravity is smaller and smaller, the exponent n becomes smaller and smaller and smaller. And in the end, when Rayleigh number is very small, it's a conduction problem, and we don't have to any dependence on Rayleigh, right? And this is what we see. If you go to Rayleigh 10 to the minus 10 to 10 to the minus 2, 10 to the minus 10, you realize is essentially 0. These guys have a 22 order of magnitude span in their formula. It's pretty amazing, 22 orders of magnitude. The slowest experiment was whatever number, and the fastest experiment was the same thing with 22 more zeros. I actually don't know how they managed to do that. In our lab, we can barely do 4 orders of magnitude on a good day. 22 orders of magnitude, yeah, that's impressive. So, and when we see for really small Rayleigh numbers, if we were to calculate Nusselt, we would get a value of 0.2 to 0.5. And if you remember, for Rayleigh essentially 0, this would give us 0.36, this 0.6 squared. So it's right in the middle of this. But that is when it's becoming more of a conduction problem. From the point of view of plug and chug, get the Rayleigh, and use this table, this formula and this table, or get the Rayleigh and Prandtl and use the formula and this formula outright. In the exam, I will tell you if I want you to use one or the other formula. And the same thing can be done for spheres. This is very much the same as what we did for external flows. The only difference, the flow is not externally imposed, it just comes from buoyancy. And when Rayleigh is exactly 0, the Nusselt is exactly 2. And this does come from solving the equations of conduction. For a sphere, there is a steady state solution for 0 velocity that was also tabulated when we looked at the dimension heat transfer, dimensionless heat transfer coefficient and shape factors on the week, what was that? Week 6 of class. Very, very interesting. From the practical point of view, plug and chug, get a Rayleigh, get a Prandtl. And you calculate Nusselt, then you unpack Nusselt. Of course, you have to check that we're in the right Prandtl number and the right Rayleigh number that has been verified experimentally. So that was external flows in natural convection. We saw the plate, we saw the cylinder, we saw the sphere. Now let's talk about internal flows in natural convection. For example, if I have in a chimney, say if I have a pipe and I heat up the pipe, the flow is going to want to move up, right? Much like in a chimney, it's going to have a draft, and we can calculate that. So although this schematic from the book is for a pipe that is at an angle, I'm going to discuss only vertical internal flows and horizontal. So in this vertical internal flow, we have the same problem as before. We have an entry length and a fully developed flow. And as you can imagine, in the entry length, we have high heat transfer, intense heat transfer. And in the fully developed flow, we reach a steady state in which the convection coefficient doesn't change anymore. Let's see, these formulas look somewhat scary, but let's start with this formula 939 that is that I'm indicating here. By the way, these slides, this part is not in the handout we typed, but I uploaded it as supplemental materials in this unit in E-class. So you have all these slides too. So in fully developed flow, so from here upwards, right? In fully developed flow, we can calculate the Nusselt number when this is a vertical channel, and it is Rayleigh over 24 multiplied by S over L. S over L is some sort of aspect ratio of this channel. F is the width and L is the length. So for example, we can have two plates that are vertical, separated by a distance S and a length, a height L. And depending on the temperature of the fluid coming in, this case is T infinity, the room temperature, and the temperature of the plates, right? Let's call it TS1, is going to tell us how much heat is exchanged. Something interesting to connect things is in internal flows, with forced convection, we used to have a mean velocity and a mean temperature, Tm or Um. But now we don't. Now we have temperature of the plate and temperature of the fluid around. So this is when we have fully developed flow and both plates are hot. When only one of the plate is hot and the other is adiabatic, that means it's insulated, the Nusselt number would be half of that. And of course, makes sense because we have only one plate. So far, these two are easy to calculate, even easy to make sense. This one on top looks more complex, but if we work together, you're going to see in reality, it's not such a big deal. You see this bracket here that says 1 minus exponential of something? Okay, let's forget about this bracket for a second, and let's look at the front. It's 1 over 24 Rayleigh S over L. That's what we have here. So this is the fully developed value. And let's look at this other part here. And it says 1 minus exponential of something, right? This that is inside the brackets is the heat transfer, is some sort of a correction factor derived analytically for the entry length. And what it says is that the Nusselt is much higher at the entry, at the Nusselt is much higher in the entry region than in the fully developed flow. And what we need to calculate it is Rayleigh, that is the same as we knew before, and S over L, same as before. So Rayleigh times aspect ratio width between the plates over length gives us the characteristic length of this entry length. So we can calculate lots of things, right? We can calculate quite many things now. Let's talk about enclosures. So we discussed just before was flow between two plates. So in one end, flow comes in, and in the other, flow comes out. They are not capped. This is more or less like a chimney. In an enclosure, it looks almost the same, except now they are capped. So the flow cannot come in and out. The flow is trapped. And as we add heat to this flow, or you take heat away, there are going to be flows. But because it's a closed system, right? There is no mass coming in or out. All the convective flows are going to be inside. So you guys have an idea, this is very much what happens also in welding. You melt the metal, and in some processes, you do not add any more metal, and the flow starts to move like crazy inside the weld with nothing coming in and nothing coming out. But that motion makes a lot of difference. To give you an idea, in the case of welding, if we have this fluid motion, we would be enhancing heat transfer, and we can make a weld either wider or deeper. And people have worked on this so much, and there are special formulations of alloys just to manage these recirculating flows. So let's talk about what happens in an horizontal enclosure. And this horizontal enclosure would be, for example, you don't need to have a surface. You can have like for example, a flat plate of water that you heat from below. If you heat it from the top, we already discussed. Hot is above, cold is below, nothing happens. But if we heat it from below, what is hot at the bottom wants to go up because it expands. And the way things go up in a horizontal shallow enclosures is very interesting, because is this like what they call self-organized criticality. They generate convection rolls that are like gears in a machine. One, for example, in this roll here, I'm indicating heat goes up and causes one roll to flow to the right and another roll to flow to the left. And then there is another roll, another pair of rolls in which the hot goes up and the cold goes down in such a way that, much like gears, they are always working in sync, right? In the book doesn't say, but you can even predict the size of these rolls. And one of the approaches to turbulence is to say, okay, depending on how big my Rayleigh number is, I'm going to have smaller and smaller and smaller rolls until I have a chaotic motion of turbulence. So in the case of a shallow enclosure, the Nusselt number is given now by this expression of Rayleigh and Prandtl. Look at the small exponent of Prandtl. It doesn't really vary very much, but here we have Rayleigh to the 1/3, as we're familiar with. And it's an exponent times Rayleigh to a factor times Rayleigh to an exponent. An exponent is kind of well known. What matters here is that we would get this Nusselt, and L, remember L is this thickness of the enclosure. In this case, the thickness of the enclosure. So we get a Nusselt based on L, and from here we can calculate a convection coefficient for the heat going across these many convection rolls. This formula looks like trivial. The physics of this problem are extremely difficult. This is what mathematicians love to do for a living. And all we do is this. And guess what? With this, you can design machines. All the rest of mathematics is good for them. I don't know for who else. But with this, you can cut across this extremely difficult problem. If the enclosure is vertical and we have one wall that is cold and one wall that is hot, such as the case of a two-pane window, a double pane window, so we can generate a recirculating flow. This would be a single flow, right? That goes up on the hot surface and comes down on the cold side. This is what they call a cellular flow, right? If the Rayleigh number is less than 1,000, and by the way, that's the case for windows, you can check it out, you have no flows. And in this case, the heat transfer would be by just conduction, right? If Rayleigh is less than 10 to the 3, you just have a conduction problem, as we have done when we calculated windows. If you might remember, when we calculated a double pane window, we assumed that the air was behaving much like a solid. We were not accounting for boundary layers inside. That's the case of a window. If the Rayleigh is bigger than 10 to the 3, we would have these boundary layers and correlations to calculate. And very high Rayleigh, we would have turbulence inside. Not the case of a window. In a window, we don't want turbulence, right? Because we do not want to exchange heat. It's exactly the opposite of a heat exchanger. So let's stop here. These are the formulas to calculate heat transfer across the two panes. I propose we stop here, and we're going to wrap up on Friday, and hopefully we'll start with heat transfer with phase change. Thank you, everybody. I'll see you on Friday.
I have a question.
Yes.
Friday's a holiday. Do we
Oh
still
God.
have class?